Good morning. This is your stats sensei, Mr. Spensei, and I'm going to be going over the extra credit test A. This will be problems 1 through 10. This is going to be a long video. I hope it's very helpful to you. So, which of the following is a key distinction between well-designed experiments and observational studies? Remember, in an experiment, um, we assign treatments. In an observational study, we're observing people doing what they already naturally do. Experiments can show causation, and observational studies cannot. So let's look at our answer choices. More subjects are available for experiments than for observational studies. This is false. More people are available for observational studies because they don't have to have treatments assigned. We don't have to have agreements, etc. Ethical constraints prevent large-scale studies for observational studies. Um, and that's false. Ethical constraints prevent large-scale studies for experiments because we can't always assign people to the new drug or something. We have to have people volunteer. Experiments are less costly. That's false. Experiments cost more. An experiment can show a direct cause and effect relationship, whereas an observational study cannot. That is true because experiments have treatments assigned. Tests of significance cannot be used on data collected from an observational study. This is false. We can run tests of significance on both observational studies and experiments, but with an observational study, we show relationships or correlations. We can't show causation. We can only show causation with an experiment, but I can definitely run a test of significance. So I can run a test of significance for both. So that's really important to know. All right. So a manufacturer of balloons claimed that P, the proportion of balloons that burst when inflated to a diameter of up to 12 inches, is no more than 0.05. So what they are claiming is that P is less than or equal to 0.05. That's their claim. Some customers have complained that the balloons are breaking more frequently. All right, so they're claiming that it's greater than 0.05. All right, if the customers want to conduct an experiment, they want to conduct an experiment to test the manufacturer's claim, which of the following hypothesis would be appropriate? So my going in is they are claiming P is less than or equal to 0.05, but we can't use that. We can only use the equals to 0.05 because that's always an equal sign every single time. And then the alternative is what they're claiming that the customers are saying it's more frequent than 0.05. Remember, this is always equal, and we're claiming that it's more frequently, or that was what we'd be concerned about. So in this case, our answer choice is B. All right. And I guess I should have said anyway. So moving on. Lauren is enrolled in a very large college calculus class on the first exam. The class mean was 71. So exam 1 had a mean equal to 75 with a standard deviation of 10. On the second exam, exam 2, the class mean was 70 and the standard deviation was 15. Lauren scored an 85 on both exams. Assuming the scores on each exam were approximately normally distributed, on which exam did Lauren score better relative to the rest of the class? They told us it was normal, so we could use a normal curve and do a normal CDF, but I don't intend to do that. I intend to work through this using a z-score. So with the z-score, we have z equals x minus mu over sigma. So in this case, we have equals 85 minus 75 divided by 10. So once again, at this point, that's 10 over 10, which is 1. So her z-score is 1. Over here, we have a mean of 70 Her score is 85 still. And so we have 85 minus 70 over 15, which it gives us z equals 15 over 15, which also equals 1. So in both cases, she had a z-score of 1. So she scored about equally well on both exams. All right. On the next one, question number 4. Suppose that 30% of the subscribers to a television cable service watching the shopping channel at least once a week. You are to design a simulation to estimate the probability that none of the 5 randomly selected subscribers watch this shopping channel at least once a week. Which of the following assignments of the 0 through 9 would be appropriate for modeling an individual subscriber's behavior? All right. So in this particular case, we have 30%. That's the key word, and we're supposed to do a simulation. So we could have, and we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 10 numbers, and 30% of 10.30 times 10 tells me that I need 3 numbers, and it can be any 3 to represent. Well, I could choose 0, 1, 2, 3, I could choose 7, 8, 9, or any combination. But if I assign 0, 1, and 2, that would work. And the reason I chose that is because it says assign 0, 1, and 2. Well, that's 3 out of 10, or 30%. So my answer choice for number 4 is A. Number 5, the number of sweatshirts a vendor sells daily has the following probability distribution. All right. So this should probably go into L1, and this should go into L2. And then ask if each sweatshirt sells for $25, what is the daily total dollar amount taken in by the vendor? So what we're doing is we're essentially going expected value equals 0 times 0.3 plus 1 times 0.2 plus ... plus 5 times 0.02. And I should have entered this in my calculator already, but I did not, so I'll go get that done. Stat edit, clear some stuff out, of course, because I didn't think about it. All right, so when I go to enter that in, I'm going to put in 0, 1, 2, 3, 4, 5 into L1, 0, enter 1, enter 2, enter 3, enter 4, enter, and 5, enter. Then I'm going to go to L2, and I'm going to put 0.3, 0.2, 0.3, 0.1, 0.05, and 0.02. So I do a stat calc 1 var stats. My X list is an L1. My frequency is my percentage, which is going to be L2, so second 2. And I end up getting about 1.44 shirts. So the expected value is about 1.4432. But they asked me what was the expected dollar amount. So I need to come back and multiply that value by 25. So 1.4432 times 25. And I end up getting 36.08, which I see that I don't have in there. So I must have had some sort of data error. So let's go back and figure out what that is. 0.3, 0.2, 0.3, 0.1. Not 0.05, 0.08. There we go. Stat calc, 1 var stat. And this should not be one that. This should be 1.52, which is a much better number. So 1.52, and then I'm going to multiply that by 25. So 1.52 times the 25 equals $38. And so for number 5, I end up getting D. The correlation between two scores X and Y equals 0.8. If both the scores and the Y scores are converted to Z scores, then the correlation between the Z scores for X and Y would be, okay, it doesn't matter. Z-scores, here's what you need to know. Z-scores are not impacted by adding or multiplying. So Z-score, if you add a constant, Z-scores aren't impacted. If you subtract a constant, Z-scores are not impacted. So the relationship between them will remain the same. So in this case, correlation is 0.8. So guess what? Because the z-scores aren't impacted, the correlation doesn't change, and number 6 is going to be E. Suppose that the distribution of a set of scores has a mean of 47 and a standard deviation of 14. If 4 is added to each score, what will be the mean and standard deviation of the distribution of the new scores? So in this part, we're talking about adding constants. All right. So if I add 4 points to everybody's grade in the class, the average will go from a 47 to, we add it to 4 points. We can add constants to measures of center. So since we can add a constant to measure of center, we're going to end up with a 47 plus 4. The mean will be 51, which gets rid of these. But with measures of spread, we cannot add a constant. We cannot add 4 to the 14, so it just remains at 14. So here's our answer choice, and here's why. If the range of the class, the lowest score had been a 60, and the highest score had been 100, we'd go, okay, the range is 100 minus 60 equals 40. But if I add 4 points, this now becomes 104. This becomes 64, and the spread is still 40. So adding constants will not change measures of spread. All right, number 8. A test engineer wants to estimate the mean gas mileage in miles per gallon for a particular model of automobile. 11 of these cars are subject to a road test, and the gas mileage is computed for each car. A dot plot of the gas mileage values is roughly symmetric and has no outliers. Please remember, this is coming from the sample. The mean and standard deviation of these values are 25.5 and 3.01. So this is my X bar, and this is all coming from the sample, respectively. Assuming that these 11 automobiles can be considered a simple random sample of cars of this model, which of the following is a correct statement? Well, we need to know our formula. X bar plus or minus T star S divided by square root of N. Well, we know X bar is 25.5 plus or minus. We'll come back to T star, and we know this is going to be 3.01 over the square root of 11. That gets rid of these right now. So now we're just looking at how can we do this? And we're going to go second vars, inverse T, 1 minus 0.95 divided by 2. Our degrees of freedom are 11 minus 1. And I end up getting 2.228. All right. Remember, degrees of freedom for one sample T are n minus 1. All right. That's not true for everything, but for one sample, it's n minus 1. So we end up getting A is our choice. Number 9. A volunteer for a mayoral candidate's campaign periodically conducts polls to estimate the proportion of people in the city who are planning to vote for this candidate in the upcoming election. 2 weeks before the election, the volunteer plans to double the sample size. The purpose of this is, all right, bias can only be removed from a study by having a well-designed study. And changing the sample size will not impact bias. All right, so that gets rid of A and C. All right. Reduce the effects of confounding and variables. That really has no effect on that. Increasing sample size doesn't reduce that effect. Decrease the variability of the population. the population's variability is what it is. Because that has the word population, we can't mark that. If it had decreased the variability in the sample, yes, it would, but not in the population. We can't affect the population. It is what it is. We can only impact our sample. Decrease the standard deviation of the sampling distribution of the sample proportion. And that is possible, and here's why. If we consider this, our formula for a confidence interval would be P hat Q hat over N, with this part right here being the standard error or standard deviation. If I increase N, this section gets smaller. So because this is getting smaller, we are decreasing the standard deviation. So the answer to choice to this is E. The lengths of individual shellfish in a population of 10,000 shellfish are approximately normally distributed with a mean of 10 and a standard deviation of 0.2. All right. We're centered at 10. And then we can go 1, 2, 3, 1, 2, 3. And all of these would be going, that'd be 10.2, 10.4, 10.6, so I'm adding 0.2. Which of the following is the shortest interval that contains approximately 4,000 shellfish? Well, first off, if we want the smallest interval, we're going to need to be centered on the mean. So it's really key that you remain centered on the mean. All right. And we want 4,000. So we want 10. So 10,000 is what we have total, and we want 4,000. And if I divide that out, that ends up being 0.40. So I need some value in the center here that represents about 40%. Okay? So there's a couple ways to go about this, but basically I need to find about 4,000, and I can do this a couple different ways, but I'm going to sit there and look at the ones that centered on the mean. So I'll take this first one. This is not centered on the mean, so I can skip it. This is also not centered on the mean because it's above, it's below it, all right, because it's 9.74 to 10. So that's not centered. This one looks pretty centered on the mean, so I'm going to guess that one is a starting point. Now I'm going to go second vars, norm, CDF, and I need 9.744, upper 10.256. And in this case, mean of 10, standard deviation of 2. And I get about 0.101. Well, that means that area right there is 0.101. That's not big enough. If I'm okay, so not big enough. So not doesn't look like that's going to work. Then I go and look at number 10. I mean, look at D. All right, so we're going to do the same thing. We're going to go second vars, normal, CDF, and I have 9.895, and I have 10.105, and I have 0.04. All right. And if I 0.04 and I come back and multiply that by 10,000, I end up with 418. I have to pause this for just a moment because I've run into a slight problem. All right, so found my error. I have standard deviation of 2, and it should be 0.2. And there we have about 40%. All right, so the one that gives us 40% or close to it is D. Let's go back and look at C real quickly. Second vars, norm CDF, lower bound 9.744, 10.256. And I end up with about 80%, 79.9%. So that's not close to 40%. And if I check out E, I go second vars, norm CDF, and I will have 9.92 and 10.08. And I end up with 31%. So this is close to 80% or 79.9. This is close to 40%, and this is close to 31%. And the reason I knew that I needed 40% because I had 4,000 shellfish out of a total 10,000. So 4,000 divided by 10,000 is 0.40. So my answer choice to this was E. All right, we got 3 more of these for this one. Thanks for watching. Hope to see you on the next one.